Hello and welcome to this out of order, out of everything lecture. I've learned that some of the things that we said about waves were not as straightforward as I would have expected. So we're going to have a general lecture on waves. And this is going to be about general concepts that will apply to plasma physics, but not only to plasma physics. And in fact, where we're going to start from is electromagnetic waves in the vacuum. That's all that we need to see the concepts that we are using and we are needing in plasma physics. If you prefer, we can call this free space instead of vacuum. Now, since we're in free space, there is not going to be any macroscopic current or any charge density, and therefore Maxwell's equations, I'm going to go quickly on this part because this really I know, you do know, can, in their differential form, can be simply written as I'm doing now. Divergence of V is equal to 0. There is no charge. Divergence of B is equal to 0. Del cross E is equal to minus dB over dt. And del cross B is equal to 1 over c squared del, dE over dt. And you know what, I mean, how this works. Take the time derivative of make numbers. Here of equation 4, and that gives us that changing the order of the derivatives, del cross dB dt is equal to 1 over c squared d 2e over dt squared, from which replacing del and cross e for minus b over dt, del cross e is equal to minus 1 over c squared d 2e over dt squared. But del cross E is equal to the gradient of the divergence of E. This is a vector identity. Use the plasma formulary if you've never seen it before, minus del square of E. This is true for any vector. And of course, this term by Poisson's equation is 1. Sorry, the equation 1, Poisson's equation is 0, not 1. And therefore, we obtain that del square E is equal to 1 over c squared d2e over dt squared. And pretty much in an identical way, you can obtain where I'm using numbers to type more quickly, that del square b minus 1 over c square d2b over dt square is equal to 0. Now, these are vector wave equations. And since they're identical, we can worry about solving them only once and replace E or B with a generic scalar psi. And the reason why I'm using a scalar is that psi is going to represent any one of the components of the fields. Clearly, those equations, 5 and 6, those wave equations apply identically to each component of the fields. Since these are linear operators, they apply to vectors, and the x component of, for instance, E is determined by a wave equation just for that component without mixing with anything else. Okay. I should clarify that in general, psi is psi of R and T, but I can also work more easily just with one coordinate. And let's see how we can. Okay, what we're going to do is to look at transverse plane waves. Oops, let me spell plane, yes. Sorry about that. In for transverse plane waves, both E and B are on a plane that is perpendicular to the propagation direction, and only depend on the perpendicular distance from the origin to this plane, and of course on time. Now, the plane let me type it here. Oops, I don't need this to be. Make this bold. That's, and that plane is our wavefront. Now, let's see if I can make this readable. I'm going to define just need to find the correct symbol. Okay, just give me a moment. Okay, found it. The Greek zeta, or consistency with the reference I'm using, and that's the letter I'm going to be using for the distance from the origin to the wavefront. Wavefront, and I'm going to use the vector k as the unit vector perpendicular to the wavefront. Here we go. And maybe I can call it k hat here. That's going to be my unit vector. That means that k hat dot r is equal to zeta. The reason why I needed the symbol is that you will never know what I'm writing here, even though I'm telling you. And on a given wavefront, this is going to be a constant. A wavefront is a plane of constant. Zeta. And then I can also get the direction cosines of the unit vector k hat from my Cartesian coordinate system as k hat dot x hat, k hat dot y hat, and so on. Now, the vectors E and B are constant along the wavefront, which again is normal to k hat. They only vary in the zeta direction and time. That means that the nabla operator del can be written as follows, as x hat partial with respect to x plus y hat partial to respect to with respect to y, and plus z hat partial with respect to z. Okay, now that allows us to see that if we look at the way the wave really behaves, we realize that that's actually a one-dimensional wave because of the direction it propagates in. Sorry, so one-directional wave equation given by second derivative of psi with respect to zeta minus 1 over c squared second derivative of psi with respect to time equal to 0. And of course, you know what the general solution of this equation is. Psi of zeta and t is equal to a function of zeta minus ct, that's a forward moving wave, plus a function of zeta plus ct, that's a backward moving wave. Or if you prefer, f is a plane waveform propagating in the positive zeta direction, and g is a waveform propagating in the negative zeta direction. And the velocity of propagation is, of course, c, which is the speed of light, which I've not said anywhere, but you do know that. C squared is 1 over epsilon naught mu naught. Okay, so that's that for plane waves. Now, I took a moment to think about how much we can really go through in this class. Well, let's keep it within what I would call reasonable limits. So first of all, the next thing we're going to do is to introduce the simple harmonic waves. Remember, let's see, this is the general solution, and I lost track of my numbers. Let's call this 7 for my wave equation. One possibility is to just pick a wave that is propagating in the positive zeta direction and write it as psi of zeta and t is equal to a and just amplitude times the cosine of k, where k is now a scalar, zeta minus c times t, which I can also write as a times cosine of k zeta minus k, sorry about that. I want the k first, k omega. No. K times c, which gives me omega times t. And in here, I'm pretty much defining omega that just by dimensional analysis, clearly that's going to be the angular frequency of the oscillation, while k is the wave number of my waves, wave or a propagation constant. And you know how to get the wavelength and the period. Wavelength is 2 pi over k. The period is 2 pi over omega. That's 1 over the frequency. And typically, we refer to the angular frequency as frequency. That's a bit of a sloppy notation or abuse of notation, but that's what we do just to save some breath. And we can also define k as k times k hat, where k hat was the direction normal to the wave front, and this is going to be my propagation vector. Okay, now, in principle, I can see, well, my zeta was equal to k hat dot, let me make clear that this is a hat. k hat dot r, by the equation above, k hat is k over absolute over norm of k. So let me write that's 1 over k dot r. And that tells me that wrong arrow, sorry about that, that psi from the equation, unnumbered equation above, call this 8. Psi now of r and t is going to be equal to a times the cosine. I want kz, that's k zeta, that's k vector dot r minus omega t. Okay, what is to be learned from here? Hopefully something useful. And here is what I want to bring your attention to, because this is one of the things that we really want to address with this lecture. Planes of constant the planes or constant phase are defined by the condition k dot r minus omega t, which is the same as k zeta minus omega t. This needs to be constant. Okay, so if this is the plane where the phase is constant, I can define the velocity with which this plane moves. Try to make it a little nicer. The velocity with which a plane of constant phase moves is called, no surprises, the phase velocity. And you can see it from up here. All I have to do is take the derivative with respect to time of equation 3.5. That is d zeta dt. That's going to be my velocity of the plane defined by equation 5. That's taking the derivative is just going to be equal to omega over k. And that is where the phase velocity comes from. Let me emphasize this. That's pretty important. Actually, I'm going to change my box here. I'm going to make it higher level box. Right pen, okay. Okay. Now, if the wave is forward moving, progressive wave, then the phase velocity is positive. If that is, it moves in the positive zeta direction. If we're taken wave moving in the negative zeta direction, we would have obtained also that the phase velocity would be negative. And one more thing that I doubt whether I should say or not, but I'm just going to say regardless, is okay, so this was part one. The following, that is the use complex quantities. Yeah, let me just quantities or notation, if you prefer. And here is how it goes. I'm going to write my wave as psi of r and t equal to a times the exponential of I times k dot r minus omega t. And here you kind of see where the opposite signs for k and omega come from the fact that if omega is positive and k is positive, the wave is going to move in the positive direction with the minus sign. And of course, physical quantities are real, so you always have to take either the real or the imaginary part. You do your Fourier thing, you know how to write differential operators. And you know how to write the Maxwell's equations in this notation. I'm not going to distinguish between real and physical space in my notation, but you should not have any doubts about which is which. The divergence of V turns into K dot T, divergence of B turns into K dot B, and K cross E is equal to omega times B, and K cross B is equal to minus omega over C squared E. And I lost count again. Just let me number them. 12, 13, 14, and 15. From 14 and 15, sorry, from 12 and 13, see that k dot e is equal to 0 means that E is perpendicular to k. K dot b equal to 0 means that B is perpendicular to k. And that is the reason why these waves are called transverse waves. So that was pretty much all I really wanted to say about this part. Or actually almost. Notice that the three vectors E, B, and K, taken in that order, constitute a right-handed orthogonal set. And you can see it from the equations 14 and 15 that E is also perpendicular to B. Sorry, when B is perpendicular to E and E is perpendicular to B. So that's why we get this to be right-handed orthogonal set by not in the rotation of coordinates. Just be careful, of course, as always, with the order you take the cross products. And I think that should be all that we should care about. There is more. And in fact, this would be a good place to talk about polarization. But I'm going to cut it short here and move to the last piece that's really relevant to us. Well, really, not that polarization is not important to us, but there is a limit to how much we can say. And in fact, this would also be a good place to talk about energy propagation and Poynting vector. I hope you've seen in E&M how to build the physical Poynting vector from the complex notation. But time is short. And so what we're going to talk about instead is wave packets. Okay, what we've seen so far is, what we discussed so far is a single wave with some frequency and k and the speed of light and all of those nice things. But in general, I may have a superposition of plane harmonic waves that are all propagating in the same direction, zeta, but with different amplitudes. And the idea is that I'm going to have a number of, or an infinite number, if I do this in continuum, of waves with similar values of the wave number, only spread a little around the central reference value. in other words, in symbols, my wave psi of zeta and t is going to be equal to the integral over all values of some amplitude, which is function of the wave number times the harmonic wave with that wave number. So I k zeta minus omega. That omega is a disaster. Let me do it again. Minus omega times t. And the integral is, of course, in the k. Where the idea is that a of k is 0, far from some central or reference value k0. So that's the idea of the packet. The packet is centered around that central wave number. And I should emphasize that this also corresponds to a small spread in frequency or angular frequency. Around some central value omega 0. Now, there is going to be, that's the case because for any wave, there is going to be some relation between k and omega, the dispersion relation, called with a name for a good reason. Okay, we said that the amplitude A of k is centered around some value k0. That means we can use the dispersion relation, whatever it is, to calculate omega as a function of k. And therefore, k is, in this sense, is our independent variable. Now, what we can do is, I'm just thinking how deep we want to do. Well, what you do is to take Fourier transforms and use properties of the Fourier transform to calculate A of k. And I'm not going to do the math. I'm just going to write the result. That's going to be 1 over 2 pi or square root of 2 pi, depending on how you define it. In the textbook I'm following have the 1 over 2 pi notation. So it's going to be psi of zeta and 0 times e to the minus ik zeta in the zeta. And so that's the amplitude of time t equals 0. And I could say, well, I can do the same thing for the amplitude as a function of omega instead of k, and I get it in the same way. This is going to be the integral minus infinity plus infinity of psi at 0 function of time, e to the I omega t in dt. Notice the difference in sign is as usual because of the different convention we use for k and omega. Now, we're going to assume that this function in the first expression, this function is 0 if k is far from k0. So we only care, all that matters is what happens in some range. Let me write it next line. K sub 0 minus delta k less than k less than k0 plus delta k. This in general does not strictly need to be symmetric, but that's not making it more complicated than it needs to be. We're getting there. This may seem like, what on earth are we doing? Well, it's in space, on Earth, but it does. Hopefully, it will make sense. It does make sense if you spend enough time to think about it, and that's the great thing about the recording. You'll have time to look at it, think about it, and think about how much better we could have explained this. All right, jokes aside, our next and pretty much last thing to do is to make an important assumption. And what I'm going to assume is that omega as a function of k is a smooth, slowly varying function of k. Then I can say, well, okay, if that's the case, I can Taylor expand omega. Omega of k is, with good approximation, equal to omega 0 plus k minus k naught d omega dk calculated at k naught. Now, what is the phase factor in our wave equation, the place where we started? And that would be equation 16. Wave factor is the stuff that's inside the sine or the cosine, or in this case, the exponential. That was, I just looked at it and already forgot, equation 16. Let me put this in writing. Wave equation 16. What I'm going to do is to replace omega with this expression that I just wrote, and I'm only going to do it for the wave factor. I'm not going to write the whole thing. What I have is k zeta minus omega, which is omega of k times t, That gives me k0 zeta minus omega 0 t plus k minus k naught. Sorry, got carried away. Zeta minus d omega dk at constant k naught, or at the value k naught, sorry, times t. From which I can say, well, okay, I see what's happening here. I have this factor. That is what I would have in at the center of my wave packet. Then I can say, well, psi of zeta and t is going to be some psi sub m. I'm going to tell you what the m stands for in a moment, which is function of zeta and t. That's a comma, not some obscure symbol. Zeta and t times the exponential of I k0 zeta minus omega 0 t. Where psi m is everything else. All right. You may be starting to despair, but I know we're close to the conclusion. That's what gives me hope. Okay. This is the integral between k0 minus delta k and k0 plus delta k. Of a of k times the exponential of this mess up here. Let's see, I probably need a bigger bracket. Okay, I k minus k naught times zeta minus d omega dk calculated at k naught times t, all integrated in dk. Okay, so what do we have is a wave packet psi. Let me square these two. I'm squaring together because I wrote them too close to each other. And let me give the numbers. Equation 17, psi is a wave packet. It's carried by a carrier wave with frequency omega 0 and wave number k0 that is modulated by the amplitude function psi sub m. So psi, the m stands for modulation, which is function of zeta and t. And here is the key step, so pay close attention. The phase of constant packet amplitude is given by the relation zeta minus d omega dk calculated at k0 times t equal to 0. That's the if I set this equal to 0 or to a constant. Regardless of where I am in space and time, I'm going to see the same amplitude, the amplitude, the original carrier. And then I can ask the question, what velocity does this special constant amplitude propagate with? Well, I just take the derivative. The zeta dt equal to the omega, partial omega with respect to k, calculated at k0. And this quantity is what is called the group velocity. And notice that no. Let's call this 20. I can write this in terms of the phase velocity. Group velocity is d omega dk k0, but omega is v phase times k. Okay, I need a straight line here. Derivative with respect to k, calculated at maybe a square bracket, calculated at k0. Come on. No, sorry. Good. And this is v phase at k0 plus k0 derivative of v phase with respect to k, calculated also at k0. And let me box this too. Now, a couple more things and we're really done. If the medium is such that the phase velocity does not depend on k, that is, if omega of k is linear in k, when I take the derivative, sorry, when I do omega over k, I get a constant. And when I take the derivative, I get the same constant. So the group velocity is the same as the phase velocity. In that case, the medium is called non-dispersive, which is the case of free space, for which omega is k times c. If I take k omega over k or the omega dk, I get c. If the phase velocity instead decreases for increasing k, that is, the derivative of the phase velocity with respect to k is negative, then the group velocity is less than the phase velocity, and the medium is said to be normally dispersive. And the opposite case, where the derivative of the phase velocity with respect to k is positive, then the group velocity is larger than the phase velocity, and the medium is said to be anomalously dispersive. Now, important thing, in many cases, the phase velocity of a wave in a plasma can be larger than the speed of light, which is always a baffling result. We didn't do anything wrong with the math. It's not a mistake. The fact is that the information is carried by the carrier wave, which travels at the group velocity. And that the group velocity, that is always going to be less than the speed of light. If we find that the group velocity is larger than the speed of light, we did something wrong. But the phase velocity itself does carry a mathematical meaning, if you think about it, while also physical meaning in the sense that it is the velocity with which we see the phase change or the constant phase propagate, but that does not carry any information. I should also point out that we did last thing. In this derivation, we did the Taylor expansion of for the wave packet, and we only kept the linear term in omega as a function of k. The result of doing the derivation in that way is that the wave packet may spread out, but it's not going to change shape. If we kept higher order derivatives, then the wave packet shape would also change with time. So the concept of group velocity is really, strictly speaking, applicable for or to and useful for wave packets where the spread in wave numbers and frequencies is small. Otherwise, that limitation of our Taylor expansion to the linear term is not a good assumption anymore. Okay, I hope this helps, and we're going to close it here, and we'll see you for whatever class whatever lecture you want to look at next. Thank you for your attention, as always.